The CubeSat team, Professor Chandra is faculty advisor. We have given this team a little bit longer time, not because they have two parts of the project, but because they have a lot of team members. And my comment was, I want you to present so that we know that everyone was busy, so that everyone had time and everyone contributed to the project. So they have a little bit longer time slot only because of the size of the team. Go ahead.
Well, hello everyone. We are the Open Orbit CubeSat team. My name is Andrew Holland. I'm program manager for the team. We are a 13-person senior design team consisting of 9 mechanical engineers, 3 electrical, and a computer engineer, as well as other underclassmen and other students working on projects. And so, I guess to start off, what is a CubeSat? So CubeSat is a nanosatellite with a specified form factor, dimensions, weight limitations that provide us with initial requirements to help develop our satellite. And so it's typically designed for students to get hands-on work with satellites. And so while most of you are aware of large satellites like the James Webb and such, CubeSats still maintain primary subsystems that those large satellites still have. Electrical power systems, thermal management, structures, power generation, etc. And so we are developing our CubeSat through 2 separate projects. And so we have the infrastructure to support it, the ground station that we call the AgSat, as well as a series of high-altitude prototype payload launches that are able to develop certain subsystems and test it in situ via a high balloon, which we'll cover later on. And quickly over budget, we have previously launched 2 altitude payloads as well as deployed 1 ground station. Each prototype payload costs roughly $700, including all materials to build it, as well as the launch preparation materials such as the balloon, helium, and such. And as well, as was mentioned about the AgSat, is that much of, we had many in-kind donations from Chuck Dewey and such to help us develop this, and so it roughly cost us $1,500. And so far, yeah, as I mentioned previously, we've launched 2 altitude payloads. So one was at the end of last semester, one was previously in this semester. The first one was primarily just get us the get our feet wet with launch preparations, what is the actual procedure for launching a hot balloon, and then this one that we launched this semester primarily tested our radio communications and power subsystems. We have 2 more prototype payloads planned to launch later next semester.
Hi, my name is Jace. I was in charge of instructors for HAP 2. I'm going to go over the requirements and specs for it. Mainly, we just needed the system to be able to operate at like -40 to -60 degrees in air temperature. These are the temperatures you can see at like 25,000 or 25 kilometers, which was our estimated maximum altitude. We also wanted the system to be able to record a variety of different states, including external temperature and pressure, as well as internal states, including internal component temperatures, as well as the battery voltage and current draw from the battery. We also wanted the system to be able to record the entire ascent and descent, which meant it needed to have battery power for all the way through pre-check, ascent, descent, and we didn't really plan on getting all the way through landing because we weren't sure how long that was going to take. So we did want to opt for a way to track the system with and without power. We opted for the GNSS breakout, which allows us to record our payload's position, whereas the spot tracker is more of a self-sufficient package that allows us to track it no matter what. For our main design, it consisted of a 3D printed structure. This allowed us to house all the components and just secure everything, whereas we used a laser cut foam insulation on the outside to make sure all the components would survive at those temperatures. Our team spent a lot of time designing a custom EPS board. This allowed us to take the voltage from the batteries at 7.4 volts and step it down to 5 volts, which many of the components needed. We We then use the Raspberry Pi as an additional voltage regulator to step it down to 3.3 for any other components that need 3 volts. One of the main components we did use was a LoRa hat. This allowed us to transmit position data from that GPS PCB back down to a handheld receiver. The handheld receiver is one of the first things that we tried on launch day. It included just plugging it in, making sure our software was running, and it could communicate with the payload. Once we had attached all the flags and flyers and posters to our payload to make sure everyone could see it and track it, we launched it.
Yes, and our launch day, October 18th was a fun weekend for us. Finally had a successful launch. Our balloon reached up to 26 kilometers in the stratosphere. It went across 250 kilometers. Over on the map there, the very right side, that's Kansas over there. So that was a fun, long day for us to drive over there, but we had a successful recovery. There's a team in the picture over there, and it was all worth it. We got some great results. Nice velocity profile, consistent vertical speed. After the balloon popped, the payload actually dropped and accelerated to 100 miles an hour, started slowing down once it reached that thicker atmosphere. The ground speed, the pretty good representation of the wind speed, since nothing else is pushing against it. And as you can see, between the troposphere and stratosphere, around 10 kilometers, those wind speeds really pick up around 100 miles an hour again. For the temperature, we match pretty closely with published temperatures. It starts to deviate as the convection starts to drop off in that thin atmosphere, and the actual payload starts heating up these temperature sensors. On the descent, however, we reached more drastic temperatures. As it's falling 100 miles an hour, that convection starts to increase again, and our battery temperature starts to get a little dangerous around negative 35 degrees C, which we'll have to design for next.
So my name is Connor, and just to go over some of the stuff we gained from this. This was our second iteration for launching the balloon, and as you can see, we got quite a bit of good footage from this. It was also a great chance for us to really verify our launch procedures. Went much smoother than the first one. If you want to know how it went, just come to me afterwards and ask. It was a great chance for us to check all of ourselves against what we were doing and make sure that we were doing things right as far as making sure we were saving our data or saving our code when we were developing it. As well, we learned that we needed to do a few more system checks. We actually had a sensor failure, so we didn't get all the data we wanted to. As well, it was kind of a good gut check as far as how much insulation and heating we would need to do in the future to make sure that the system would actually survive and sort of what conditions the internals would actually see. And as you can see, we learned that hot glue is not gonna hold up at 26 kilometers in minus 40 degrees Celsius. So,
Seriously?
it was about the last thing we did before we strapped it to a balloon and sent it up, and so we'll do a little better next time. Here's another slide. And as well, we're moving on to the third iteration of our payload, which is really going to be where we take the 3D printed sort of foam structure and move it into the CubeSat form factor, where we take all the Raspberry Pi and the breakout boards that we used in the previous design and consolidate them onto our own custom PCBs and actually create a modular form factor, or a modular design that we can use to expand our design in the future.
Perfect. So my name is Ethan. I'm the electronics lead for the HAB program. To go over some more of our specific requirements for HAB 3. We're keeping a lot of the same for HAB 2. So in terms of altitude, we're also aiming for 25 kilometers greater, and the same thing with thermal, as we're still using COTS and industrial spec components. We can't really go much lower or over that. Those components cost a lot more. And the third one we're keeping is maintaining a reliable LoRa communication for the entire flight. requirements though. Instead of just sending GPS data like they would have to, we want to send all sensor and housekeeping information over LoRa at a rate of 1 hertz or greater. This is basically a lot greater bandwidth that we'll have available, which is nice. And also, instead of recording just one video, we want to record multiple HD video streams for the entire flight. In terms of modularity though, this is a big format change for us. Instead of relying on breakout boards and Raspberry Pis, we're developing our own cards essentially. It's based off the PC104 hardware standard, which is essentially what's shown in a template design, as well as a little cutout just for things like wires. But this is essentially going to be our core CubeSat architecture for this hat and future hats. So we want to make sure it's as modular and expandable as possible. So thanks to that, we have a standard mechanical footprint. We have standard pins, so we'll have like 5-volt rails available, 3-volt rails, low data rate for CAN available, as well as Ethercat, which is very nice. So these are some of the 3 boards we're working on so far. Our command and control, that's our furthest along board. That will handle all like sensor and housekeeping information as well as LoRa communication, as we want that all isolated onto one board. We also have a solar charger that's made for a feature hub, and an NVIDIA Jetson character, which will is essentially just for HAP3 processing video streams, but we're also looking into running some embedded machine learning. So in terms of processor, this is one of the also very large changes. So swapping from a Raspberry Pi to an embedded STM32L433. Main reason for this is power. Just doing basic housekeeping, the Raspberry Pi was using like 3 watts of power, which is way too much. So we're switching over to an embedded system, use about 10 milliwatts, which is about 300x power gain, power reduction there. With the STM, we also have a lot more GPIO pins available versus a 28 from the Raspberry Pi. We also have things like integrated ADCs, DACs, comparators, timers, etc., which is going to be super useful as we won't need external boards for that. So in terms of current and future work for for HAP3, as mentioned previously, we've been Jetson, command and control board, and as well as a JTAG debugging chat attachment currently being developed. We also, for HAP4, we have a solar charging board. For future work for HAP3, we're looking to refine our mobile chase car receiver, essentially throw GPS on there so we can get both the chase car's location and the HAP location at the same time. That'll make it super useful for like realistic range requirements there. We're also developing the battery board as well as a power regulator board. For HAP4, we're looking to integrate some active thermal management. So that'll include a thermal management board, as well as a high bandwidth transmitter board, as we're looking to also transmit images and possibly some low frame rate video, as well as some potential future payload boards we're still looking into. You're up to that set.
Okay. Thank you. Hi everyone, I'm Dominic. I was the ground station lead for this semester, and we're going to tell you a bit about what we've done so far these few months. So we're naming these prototypes ACSATs, which stands for Adaptable Ground Station Testing. The point of these prototypes is to rapidly test different components, especially our antennas, and see what capabilities we can do across our radio. It's really acting, this first prototype, ACSAT 1, is act as more of a learning opportunity for all of us in ground station design and get more familiar with some of the requirements that would be necessary for our future prototypes. So far, the ground station is capable of tracking current and future satellites using GNU radio and gpredict. And I want to quickly go about some of the previous work that has been done on amateur ground stations. So I'll do a huge shout out to Johan Haji, who did a open source ground station, or open source radar positioner head that we have used with some modifications. And a lot of our information so far has been gathered from the SatNox community, which is an amateur satellite tracking group. And so just to go over some of the technical work that I've done, I focus mainly more on the lead side, so developing some of our goals, some of our requirements, and figuring out really timelines that we want to achieve, as well as figuring out some of the tasks and subsystems that are necessary to create a successful ground station. Anyway, going on to some of the more unique parts I worked on, something you might not see in a different mechanical engineering design was a wind load analysis. So we were told by facilities that we cannot bolt the ground station onto the roof of the engineering building. So we have to come up with a way to create a non-invasive way of keeping it up there without tilting over. So we ended up using a plastic pallet that will not penetrate the roof, and we used some U-bolts and bolted the tripod down to the pallet. Once we created that system, I then did some research and found some of the average wind speeds that you can find here in Fort Collins. And based off that, I did some simple force balancing equations to find how much weight I would need to prevent this from tipping over, which is about 186 pounds, so not too heavy.
Tell them where it is.
What was
Tell
that?
them where it is. They can
It's
take
on the
it.
engineering building. You can actually see it from the engineering lot. It's on top of the physics building specifically. So it's up there, it's moving around. It's been successfully deployed now for the past about 30-ish days. So we've tracked a few satellites now as well. And again, onto antenna balancing. Antenna balancing was pretty cool. At first, we didn't even think of counterpoints, so we just tried to keep beefing up our motors to try to get the antennas to actually move. And we very quickly realized that no matter how powerful we had our motors, we changed our gearing, it will not move. So with the help of Tanner McKesson, down over there, purple shirt, we worked together to find out how can we actually move that center axis of mass down to where the motor shafts would be and reduce a lot of that load that was caused by that huge moment arm created. And so you can see some of the counterweights we made, which are very rudimentary, but again, prototyping. And again, once we successfully implemented those changes, we were able to move our center axis of mass, and now the ground station moves without really any problems. Next on to Michaela.
Hey everyone, my name is Michaela. I'm going to be talking a little about the custom motor to post adapter color that we fully customized. Nothing off the shelf, fit both of our motor shaft and our antenna posts. So we tapped, face drilled, and re-drilled because we were out of tolerance. We also set screw holes to ensure there was no slipping. This is definitely crucial to the pointing and tracking accuracy, because if anything's loose, it throws it off. So we definitely want to make sure that that is not loose. So we ended with a fully customizable part, which we made in the EMEC.
So my name's Chase. I'll be presenting the power system for our ground station. So here I have a one-line diagram of our power system architecture that I made in Simulink. We're primarily powering this with an AC connection to a rooftop outlet, the engineering building. Then that 120 volt AC signal gets rectified and stepped down to a 12 volt DC signal, which we're using to power our two stepper motors through our drivers and CNC shield. That also goes through a 5 volt buck converter to a 5 volt bus that we power a Raspberry Pi and camera with as well. Right here I have two pictures of our enclosure. The picture on the right was more in early development, which just shows the power components that are on this diagram here. And then the one on the left is what's actually on the roof right now, with our SDR and coax cable as well. Two things I'd like to point out. One thing I think really made this design unique is for our AC-DC converter, we actually used two converters that have a built-in parallel function with backfeed protection, which allows us to output 20 amps and 240 watts. And then I also specified to use an emergency stop button so that we could safely disconnect from power while doing any sort of testing or doing any maintenance on the ground station on the roof. So my main design requirement was I wanted to ensure that this could run 24 hours a day, 7 days a week without any power problems. So what I did to justify all my decisions was I did some load calculations, which I have here. I first looked at all of our 5 volt loads. Our Raspberry Pi and camera, as you can see, adds up to about 15.6 watts of power draw. So I made sure to specify a buck converter for 60 watts, not only to ensure that both those components are powered efficiently and there's no brownouts, but to allow for future expansion as well next semester. And then I added up all of these loads and found our maximum load of about 159.8 watts. And then I applied a 120% demand factor just to account for harmonic content in our pulse width modulation drivers. And I found a absolute maximum load of 191.8 watts, which as you can see is almost 50 watts less than the total rated secondary load for our AC-DC converters.
Hey guys, I'm Chinmay. I'm one of the mechanical engineers. And for controls, we used an Arduino with a CNC shield, as well as these two motor drivers to control the azimuth and elevation axes. And to control these, we used a special program called Rotary Control, which was an open source daemon program that we found online. And what it does is it essentially it gets the location data from gpredict and translates that into coordinates for our ground station to use. gpredict is our open source software that we use to get our two-line element data from the satellites that are orbiting around. And if we wanted to manually control the ground station, we can just use these commands right here. Capital P, followed by the coordinates that we want, moves the positioner heads to those specified coordinates. Lowercase p retrieves the current coordinates. Capital S stops the rotator. K parks the rotator. And R resets the rotator back to home.
My name is Jacob Allman, and building off what Chinmay said, the requirement that I look to solve is how can we allow a user to control this asset remotely? So whether they're at CSU or they're across the nation, being able to switch from manual control that can be done through the serial interface to software applications. The first is gpredict. This is an open source orbital propagator. Here you can see where we are at CSU, and then you can see the ISS. And so this allows you to retrieve real-time telemetry data. You can think of a TLE file as the current position and velocity of different assets on orbit, as well as it handles the overpass prediction. So really understanding that when is a satellite going to be visible, and then setting up the rotator to be able to accurately follow that. This has two operational modes. One is automated tracking, so you can select 2 or 3 assets, and it'll move to one position, wait, fall through the sky, move to the next. Or manual control, where the user can specify what they want to point at. Then looking at rotor controlled, this is the backend service that Chinmay mentioned. It's a service that allows you to open up a TCP socket and receive commands from any application, and then send those to your serial device on the Raspberry Pi. Here you have manual control, where you're directly specifying an interactive shell, and auto control, where you're opening that up, defining the port, timeout out variables. This wouldn't have been possible without Hamlet. Hamlet, there's a great amateur radio community that have a lot of these function features that are built in. Really the challenge here was how do we integrate it with our manual system?
All right, my name is Nick, and I worked on kind of configuring the computers that we used in the ground station. So I'm just gonna quickly cover those. So we used a Raspberry Pi 5 as the device that's currently attached to the box up on the roof for our antenna. Essentially, we're using it as a bridge between our remote code sending for GNU radio and general communication, and basically using that to convert it to signals being sent over serial connection to our Arduino, which can actually send signals to the motors and the SDR and that kind of data. On top of that, we also have a high gain Wi-Fi antenna plugged in, just to further ensure that the signal we receive from Wi-Fi is accurate and we don't have any interruptions. And it kind of basically serves as a client in a client server model, which we've implemented. And then our desktop, which was a picture in a previous slide, it's essentially just a server that runs programs and has a desktop environment that we can actually like visually see the commands on. And then included is a picture of the Pi itself with a heatsink and that high gain antenna. So going over the operating system, the Pi 5, in order to kind of optimize it, it only uses a command line interface, so there's no desktop environment. And on top of that, most of the scripts were written in Bash, with some written in Python. This is mainly done as Bash for smaller functions is typically faster than Python, as there's no interpreter to go through. And including that, I have an example screenshot of a Bash script which just records some metrics from the Pi itself and logs them. And because we're on the roof, there's no wired Ethernet connection, so all of our connections have to be made through CSU's Wi-Fi network. So that also required Bash scripting to configure to automatically connect every time we rebooted or logged out, logged in. And on top of that, it's also been configured using the services and timers to record metrics from the Pi itself, log them locally in zip files, and then send them over to our desktop server. And then to kind of go into the networking, one of the first issues that at least I kind of ran into was how can you get the IP of the Pi from the roof, because obviously there's no computer up there, we don't have 24 hours access, and due to how CSU's network is configured, the IP of the Pi will change eventually as the lease will expire and it will get a new IP. So the solution was to use the known static IP of our server and configure the Pi to always know that, and then every time the DHCP lease, which is what assigns our IP to the Pi, renews or reconnects, it sends the current IP to our server, This was done using DHCP hooks, which are basically just scripts that run every single time a DHCP action is performed, which would be a renewal, a connection, that sort of thing. And due to the location of the Pi itself, the connection quality varies. Being on the roof, I mean, it's just on the roof. It's a little bit further away from the access point than we would like, and as a result, we do occasionally run into issues where the network overnight just decides to stop working. But that was mitigated with the inclusion of that high gain Wi-Fi antenna, and included in the two pictures is our interfaces and kind of like a basic diagram I made to show which data is getting sent over the network. And then lastly, the metrics. So I kind of covered this previously. The Pi is currently recording its CPU temperature and input voltage of the power supply for our basic metrics. This is obviously being collected using those previously mentioned services and batch scripts and timers. So the main purpose is to kind of monitor the stability and health of the system in adverse weather. So obviously during the night when it drops down to negative temperatures, we want to make sure that it's not running into any issues relating to that. So I've included two graphs. The first one just basically shows the CPU temperature of the Pi relative to the outdoor recorded temperature from the CSU weather station over a 24-hour period. And then similarly, there's a graph that shows the input voltage over that same day, same 24-hour period, showing a trend there. And as of today, it's been running continuously for 20 days without us having to do anything really to it. So it's a major improvement.
Hey guys, I'm Saul. I'm on the RF communications side of AXAT1. I'd first like to introduce our antennas that we're using. This is our 915 megahertz Yagi. It's in the LoRa band, which means it does really well on low power and long range communication. We're going to be using this for communication with our next couple of HAP launches, as well as telemetry downlink for the satellite. Our 2.4 gigahertz parabolic dish antenna, that one's in the ISM band, so it's a much higher frequency, and we're able to do image downlink with that one. So probably in future app missions, might need a bigger one for satellite communication there. But they both have voltage standing wave ratios of 1.3 to 1, and they also have 17 decibel return loss. So that shows that both of these antennas are pretty well tuned and perfect for what we're using them for. So the 437 megahertz cross Yagi, this was actually donated to us by Chuck Dewey. We're very, very thankful for that. This one has a 1.6 to 1 average voltage standing wave ratio. It's also 16 elements long, or has 16 elements, it's 7 feet long, and it's circularly polarized. So it's perfect for satellite communication. And we'll be using that for Alto 401 prime, which has a center frequency of 437 megahertz. Since our ground station is deployed on the physics rooftop, we did a spectrum analysis using a field fox. We can see here our 3 antennas are across the spectrum as our 437, our 915, and then our 2.4 gigahertz. We can see the spectra that lies on the analysis. You can see that top one there is kind of a wideband at 2 gigahertz. It's wideband CSU network. So thankfully we're out of all the interference that comes across up there. So for modulation and demodulation of signals, we've been using GNU radio, which is kind of a flow graph type system that allows us to have building blocks for modulation on the transmit side, and then other building blocks for demodulation on the receive side. Here we set it up on a computer to have our transmit and receive with LoRa 915. We have CRC valid and header verification. So it shows that our message sent of hello world comes back parsed clearly, and we get the message. We hope to further implement this with our RTL SCR and then our HackRF as well.
Hello everybody, I'm Tanner. I worked on the structures for the ground station, but as a first year for this project, I want to talk about our market basis. And so first one is Alto University. It's the 471P. It's a 3U CubeSat, their 4th satellite that just flew last month. And their problem that they had is they needed some way to have US ground coverage. So with our ground station, we're able to provide them that communication at 440 megahertz for them as a service. And also Virginia Tech, they're a CubeSat team, kind of like us. They just flew their first satellite, the Content Cube, and they have no communication with their satellite. So again, with our ground station, we're able to provide that service for them. And our next steps.
So for some next steps, we are looking to recruit some more seniors for next year. The GS1 was our first prototype. It was kind of our prototype to iron out issues, work on anything that we needed to iron out, and then our ground station 2 is our polished version for Alta University's North American range. This is when this is our satellite to help them. So for our next steps, our team, we are presenting 2 abstracts at the end of January in Finland with Alta University for the ground station and the balloon predictor.
And a quick thank you to some of our partners in the industry before we leave. First off, Chuck Dewey, who's in the crowd with us today, is from CubeSat Technologies. He was so kind to gift us a positioner and a 440 megahertz antenna that will help to serve some of our university partners. Also Alpha Vector, they provided us their telemetry data for us to integrate into our software to process and give back to them, and in turn they're offering to hire some of our members as interns over the next semester that will lead to full-time jobs upon graduation. And finally, Unibob Space Solutions for their offer to donate us an IX-5 space satellite computer.
Yeah. I'm gonna take it over my back. Set up Yes. Thank you.